Thank you very much. I'm Miro Salem, and I lead AI and autonomous networks here at Rakuten. In this presentation, Joji and I will talk about the data platform that we are building here at Rakuten, the very aggressive requirements that we must consider when creating this telco-grade data platform. And what's also very important is the data platform as it supports an autonomous network framework. And of course, Yugabyte provides unique features, unique value propositions, which enable us to do things today that we couldn't have done otherwise, couldn't have done in the past. So at Rakuten, I have a diverse team that has a wide range of skill set from data, AI to autonomous network research. Yet we all have one common mission, and that mission is to actualize a fully autonomous network. This data platform is a critical component, if not a fundamental piece, of the networks of the future, I believe, and autonomous networks as a framework. And today we will talk about both autonomous networks as well as this data platform and how it supports autonomous networks. And Joji later will drill down into the details of all the different components and how we're putting them together to actualize this solution. Now, in my background, I've done just about every job in network operations, from drive testing to pre-launch tuning to, I work maintenance windows. I've reconfigured just about every site in the US for both Verizon, AT&T, launched the first ever LTE networks in the world, and reconfigured every single site in the US. And I can tell you that network operation is an extremely challenging task. It's an extremely challenging job, not for one person, but for thousands of people. Unlike autonomous vehicles, autonomous networks are operated by thousands of people because they're so complex. And unlike autonomous vehicles, autonomous networks have many sensors, they have many actuators as well. Autonomous vehicles, you rely on vision, maybe a little bit of sound, a little bit of hearing, and then you can steer. What you do is you steer and you hit the brakes or the gas, right? But in networks, they're just far more complicated, and it requires the collaboration of far more people, which makes it a very difficult and very challenging thing to do. So when we are considering building an autonomous network, we have to consider every part of it, and we have to consider what are the fundamental technologies that we need in order to achieve that. So before joining Rakuten, yes, I've done every job in network operations, but I've also started a company, a startup in Silicon Valley. I was founder CEO of a company called 3108, which where we built AI to automate network operations, and we had this vision of building a brain that will operate all the networks around the world. It was, by the way, we were voted the #1 AI startup in the telecommunication industry. We were selected as one of the most promising growth stage companies in the world. So while we did really well, it was still very challenging for us to actualize our vision. And that's because the telecommunication industry, the technology in it, was not fundamentally ready for the kind of disruption that we were trying to accomplish. And this is why when we talk about enabling technologies to achieving autonomous networks, we have to consider certain aspects or certain key technologies, which I will discuss with you right now. What really attracted me to Rakuten, of course, the CTO, Tarek, I mean, he convinced me to join, but also what was very convincing for me is, what was very attractive for me was the fact that it was the world's first fully virtualized network. And that's a big deal because it means that we have the foundation to build technologies that are scalable, that are resilient, that are interoperable, which are very important for autonomous networks. I mean, you hear about companies born in the cloud like Netflix and Airbnb, but Rakuten is the world's only born in the cloud a mobile network operator. And that becomes critical when we're also considering what kind of data platform is necessary to actualize the vision of autonomy within a network. And so the first challenge that we had in my startup was deploying AI in networks. Of course, it's one thing to want to build an AI to solve a problem, but it is something else to actually go through the whole sequence of events that you need to do to actually build a model and deploy it into production. It starts with first of all, it starts with a problem. Then you have getting access to data, and then having the right environment to build models, train, not just train any model, but models that can scale in production and actually be deployed into production. So it turns out that what we realized in 3.10.8, my startup, was while the vision was correct, the telecommunication industry just did not have the right fundamental technologies in place for us to be able to deploy AI, go from problem to solution in the fastest possible time. Right? So that became my mission here at Rakuten. My mission became, how do we build the question I was asking is, how do we build a platform so that I can go from problem to a solution, which is an AI in production, solving a problem in the fastest possible time. Because if I can do that, then I can produce AI at scale. I can produce a large volume of AI that then can be used as components and part of an autonomous network, which can then be controlled with autonomous controllers. So AI had to be part of the DNA. And when we talk about machine learning and AI, machine learning and AI are about solving problems that you already know, right? But what about situations where, like right now, there's a lot of noise coming in the background, situations where you didn't predict it, right? Or there are unexpected situations. How do you adapt to that? Maybe a little bit of sense of humor might help. So how can autonomous controllers or autonomous networks adapt to the unpredictable, right? When you build AI, you're building to solve a problem, but just like us humans, we have autonomy. We're able to adapt to unknown environments, to unknown problems. And so that becomes a critical question. That becomes the biggest differentiator between what's an autonomous network versus what is AI and ML. Autonomous networks adapt to the unknown. AI and ML solve specific, well-defined use cases. Perhaps it's in a very intelligent way, but they are still solving well-defined use cases. In autonomy, we don't have that luxury. And this is why Rakuten, we're big advocates of the ITU-T autonomous network focus group, which, by the way, our team, Leon Wong, is a member of our team. He is chairing that group, and they're doing incredible work. I really suggest that you actually visit the ITU-T focus group on autonomous networks, because the architectural framework of autonomy is being developed, which is using really interesting mechanisms, one of which is, one of my favorite is evolutionary algorithms or evolutionary methods of adaptation. So please check it out. Now, this is a framework for us to collaborate, but I want to talk a little bit about what is an autonomous network. When we talk about autonomous network, what do we really mean by that? And then later we will see how the data platform plays a critical part, and why Yugabyte specifically becomes essential for us to actualize the autonomous networks, and that Yugabyte does bring certain key features, and does in fact push the envelope, or create innovation that is absolutely necessary for future networks. But first, let's talk about what do we mean when we talk about autonomous networks. So this is a bird's eye view. As I said earlier, machine learning is about finding ways to bring automation to operations and via solving specific problems. But in autonomy, we're really trying to solve the unknown in operations. This image is, what you're looking at here, this is a high-level view of the architecture that represents this new level of abstraction. And it is how we plan to realize autonomy. Now, based on this architecture, I want to highlight three key components. One is in blue, which is the controllers, and that's the interface for autonomy. Evolution is the process of creativity by which we were created. It's also the process of creativity by which we believe we can actualize and build autonomous networks. And then experimentation, which is the validation of creation. It's through trial and error that we know if a particular solution is the right solution, or should we, or there's another better solution. It is that experimentation that's necessary, and it is because of that online experimentation that we find databases, components like Yugabyte critical, which we'll again talk about a bit more later. So You hear about cognitive loop or MAPE-K or OODA. They're all closed loops, and they're increasingly being pursued as mechanisms to achieve a self-contained control of a particular area or domain within the network. Here we're going to refer to them as controllers. Now, in this case, a controller is a self-contained unit in our approach where each controller is tasked with a single goal. By composing those controllers into hierarchies as opposed to peers, we're able to achieve different timescales of operations than otherwise. Now, this is the same concept as the real-time and non-real-time controllers that you may have heard about or read in ORAN. Now, in our approach, there's a slight difference, which is that there can be multiple levels in the hierarchies, as well as different types of controllers, such as evolutionary controllers. In addition to operating the network, these controllers, the controllers layer acts as the interface between existing network and the new layer of abstraction. So think of this as an abstraction. And this abstraction is the autonomy. So in this way, autonomy focuses on the manipulation of controllers as opposed to the network directly. And it is even driven by both controller and network feedback. Now, this builds on the substantial work of achieving virtualization in the network that we already have, and it makes the challenge of achieving autonomous networks a lot more focused. Now, with this new abstraction layer, obviously comes questions like how are they described? How are they represented? How do they interact with the network? And how do we ensure an interoperable ecosystem of autonomy for vendors and operators? A lot of these questions are also addressed as we are building our data platform and AI platform, and as we are building the interface between these autonomic controllers and the network, and also considering the architecture of the controllers as well as the network and the data platform. So to actualize all of this, right? I mean, there has to be a mechanism that we use to adapt, right? And one of the main questions of autonomous operations is, how do you adapt to the unknown or the unexpected? And because that's necessary in autonomous networks. So today we adapt by requiring a human to get involved and to craft a newer, better approach, right? But our challenge here is, how do you achieve this with the minimum involvement of humans? Evolutionary computing represents a codifiable way to achieve a form of creativity. In other words, evolutionary computing is a way to write down the process of creativity. And more concretely, it is a way to explore a large number of options in an efficient way. Evolution is the driver that we use to create new controllers. And how it works is another discussion. It's a longer discussion. Happy to discuss offline at a later time. But we know that we are not the only people who are pursuing this line of thinking. Google, for example, has recently applied the same approach to enable the rediscovery of several machine learning technologies by a software entity. And by the way, the end result was a much better approach than is currently known to us humans for a particular problem. I know that NASA also used this evolutional search to design radio antennas that were cheaper, lighter, and even more effective for the task than the human equivalent. So this all sounds great, but there are challenges to overcome. For example, whenever you talk about a storage space, right? The question occurs is, how long does it take? We don't have millions of years, but how do we approach this in a more effective, more efficient way? What is the right form of evolution to use? Can evolution be applied to all use cases, or is it only limited to certain use cases? I believe that it's only through trial and error that we can answer those questions, which brings us to my next point, which is online experimentation. So if evolution, creates new controllers, as we mentioned earlier, experimentation is the way that we ensure that they are fit for purpose. It's through trial and error, or we can generally validate them against the task that they're supposed to perform. Now, this is also the same way that we use to provide reliability and trust in the mechanism that is generating the controllers themselves. So when we talk about experimentation, and we talk about online experimentation, we're talking about real-time, scenarios with potentially online inferences and real-time capabilities become very important. Also, processing significant amount of data becomes also very important. Now, in the past, that was difficult to do, especially if we were trying to do this in a scalable and also reliable way. Usually, there's a trade-off between scalability, reliability, and resilience. But Yugabyte brings a new value proposition that we found very interesting that can help us in our journey towards autonomy. And in various ways, it's either through simulations or even canary testing or even sanity checking. There are different ways by which we can do online experimentation, and Yugabyte has been a key component in our approaches. So the concept of testing, it's already been shown, for example, by focus groups on machine learning in 5G with regards to the sandbox framework. So when we talk about this online experimentation, there's still also some other questions that are raised, like, how do you automatically construct experiments for migrative controllers? How do you effectively recreate a testing environment that allows me to trust the AI, that an AI created controller, for example, is going to operate in my network? What safety measures do we need to put in place to do production canary testing? All these are questions that we are addressing, and all these are also questions that we are addressing using Yugabyte as one of the technology components. The reason why I'm personally a fan of the Yugabyte technology is because it does push against previous limitations. And we need that not only in the industry, but we also need that in society. It is difficult. It's difficult to do, but it is also very important, because as we, if you look at autonomous networks as in stages, we look at autonomous vehicles, we will, you can talk about them as 5 levels of autonomy. Well, 5 is a truly fully autonomous network. As you go from one level to the other, the difficulty becomes even more challenging. In fact, it becomes exponentially harder to reach the next level. And the technologies that we have used in the past that brought us where we are today are not going to take us where we want to go. Just like an airplane can only go as high as the sky, right? It will not take us to the moon. The technologies that you've used in the past are simply not going to take us to the destinations that we aspire to go to, like autonomous networks. And this is why I am a big fan of the Yugabyte technology, because of the possibilities that it gives us, the possibilities that it creates for us in actualizing an autonomous network. And I know that let's go into the details. So specifically on the data and the AI platform. So in fact, to do that, I'm just going to give it up to Joji. Joji will talk about the various technologies that we have been working on in the background. These are technology components, and they are needed to achieve the vision that of an autonomous networks. And we'll talk also about how we are integrating them, how we are creating active deployments. I mean, that means we have to have the reliability. He will also talk about our Yugabyte architecture and how we, even if we lose a data center, we should still be able to operate flawlessly. These are all key components of a solution, and I'll give it up now to Joji to go over those and talk to you more on those. Joji, to you now.
Thank you, Miro, and hello, everyone. Now that you've heard about autonomous network, autonomous controller, and opportunities that comes with that, let's talk about technical architecture that is required to enable an autonomous network and bring it closer to the implementation of Yugabyte database at Rakuten Mobile. First, let's look at an oversimplified recipe for an autonomous network, and then we'll come back to how and why we decided to use Yugabyte database for this use case. At high level, to build an autonomous network, you need multiple data repositories to collect all the data generated by the various applications and devices in your network. you need a controller to handle operations, administrations, and management of the network. And to make the controller smarter and intelligent, you need AI capabilities. And for AI, you need data. It is like a closed loop control system that generates a lot of data and needs a lot of data processing power to continuously regulate the state of the network to a desired state without human interactions. Now, prior to joining Rakuten Mobile, I was fortunate to get opportunities to build a lot of data intensive applications and build data and AI platforms that can handle massive amount of data for other business units of Rakuten family and outside Rakuten. But there was something very unique about the autonomous network problem that was interesting for me. First of all, building something that meets the scalability, latency, and resiliency requirements for a new age telco company was very interesting. And within our network, we have different applications and devices and that generates different types of data. And often you need different types of database solutions and storage solutions for various types of data. And for an autonomous network, you need a really good AI platform that is easy to use and easy to integrate with other applications. Now you'll see with all the tools out there for AI and machine learning, ML ops is still too slow and fragmented. Iterations of AI models and collaboration of AI work takes a lot of time. If you talk to any data scientist, they will say they spend more than 50% of their time collecting data, transforming data, and integrating with other applications. The gap between model development and production grade model is so huge that most of the models that the data scientists build today does not even make it to production. It was very important for us that the technical solution that we build should solve these technical challenges in order to continuously and rapidly improve our technical capabilities and the rate of innovation within the company. We have a lot of smart engineers, scientists, and researchers in our company. Imagine the rate of innovation that we can achieve if we remove all the blockers for them to work smoothly and collaborate easily. They will be able to iterate quickly to reach the next level of maturity for our autonomous network. If you think through these challenges and the requirements, you will see some of the basic technical components that are required to implement autonomous networks are: you need an autonomous controller, you need an AI platform for faster and easier ML ops, end-to-end ML ops, like building models, training models, tuning models, and deploying models to a model serving layer. You need a model serving layer that is easy to integrate with other applications and that can scale. You need a data lake for long-term data storage so that our data scientists can use historic data to build models, run training jobs to train models using the data. And then you need an OLTP database for low latency data processing. Data lake is good for long-term storage and ad hoc historic data processing, but we need high performance, low latency database for our autonomous controller to take real-time actions based on real-time network events. Your traditional databases and Hadoop-based systems is not good enough for building an autonomous network, especially if you want your network to get all the benefits of a cloud-native architecture. Let's double-click on that OLTP database topic and look at some of the must-have features of an OLTP database for our use case. Obviously, high performance and massive scalability required to handle telco data and telco workload is a must. Then we should be able to deploy multiple copies of the database across multiple regions and replicate the data across with minimal latency for our disaster recovery and HA requirements. And the database should provide global consistency to ensure reliable and accurate data for all our applications, irrespective of the instance or region it is fetching the data from. And to enable a cloud native telco, we must ensure all the technology that we use that we are using are also cloud native. So we should be able to deploy this OLTP database on a Kubernetes cluster and should be able to use all the goodness that comes with the cloud native architecture. We want this database to be resilient and self-healing and fault tolerant in whatever ways it can. You want the network to depend on this database to support the autonomous controller. Different data applications require different types of database engines. For our use case, we wanted a NoSQL database and a relational SQL-based database to meet the requirements of all the apps that we have within the network. Now, if you know the unique features of Yugabyte, you know where I'm going with this, right? Yugabyte is the only database in the market today that fulfills all these requirements. You will find other database that meets some of these requirements, but not all. My team has looked at some relational traditional databases and tried to modify to make it work on Kubernetes. In some cases, you can barely make it work, but you are not going to get all the benefits of cloud native architecture. And you can think of deploying separate database solutions for NoSQL and SQL, but that is obviously going to be more work and more fragmented solution. For these reasons, we chose Yugabyte database as our OLTP solutions for building our platform. And the solution looks like this. Various applications and devices in our platform generates a lot of data about the network activities, which is ingested into Yugabyte in real time. The autonomous controller reads data from Yugabyte for its operations. The data in Yugabyte is also pushed into our data lake for long-term storage. Our data lake is using Miro object storage. Our data scientists will read the data in data lake from AI platform to build the model, run training jobs to train the model, and run multiple experiments to optimize the model. And then when the model is ready, it is deployed to our AI hub. AI hub is a combination of model registry and model serving layer, and it's scalable. The autonomous controller reads data from Yugabyte in real time and use the inference from multiple AI models to take actions to manage the network. As I said earlier, it is like a closed loop control system. The biggest advantage of this architecture is that it allows us to continuously innovate and improve by making our AI better and better and our autonomous controller smarter without changing any core elements within this architecture. Now, let's look at the deployment architecture of Yugabyte cluster within our platform. The deployment architecture of Yugabyte cluster looks like this. We decided to take full advantage of the cloud native scalable architecture of Yugabyte and implemented an active deployment spread across 3 data centers deployed on Kubernetes. All 3 data center clusters is acting as a single stretch cluster with global data consistency, high availability, fault tolerance built into it. In this architecture, we can afford to lose one whole data center and we will still be good. And finally, before we conclude, I want to touch on few initiatives that we are planning to do next. One of the problems that we have is data scientists spending cycles to gather data from various data sources. So one thing that we are planning to do is to build a scalable data pipeline framework that is easy to configure and deploy to extract data from any source systems. Using simple configurations, using simple configurations, you can deploy a pipeline from source to our data lake. Now, this should take away the burden of collecting data from various sources away from data scientists so that they can focus on building model and not spend their cycles in collecting data from various sources. We're also working on building a self-service data discovery and model discovery tool for fully democratizing the data and AI access, because we believe making data and AI accessible to everyone will increase the pace of innovation within the company. We're also working on an auto ML feature where engineers or analysts who are not your data scientist can use models published by data scientists and train or retrain using new data sets and use it for their specific use cases. And last but not least, we also want to scale our Yugabyte cluster to additional regions to increase the availability and resiliency of the cluster. With that, we've come to the end of this presentation. Thank you all for listening to our presentation. If you find this topic interesting and want to chat more about it, Miro and I am not too difficult to find on LinkedIn. We are also happy to answer any questions that you have. Thank you.